Hello, everyone. Thanks for coming. Today, we're going to talk about reactive programming with Java, present you some basic concepts and some libraries that you can work with Java. It's a hot topic. It's probably 5 years from now. It's pretty recent. I think that some of you may already have heard about it, and I believe it's a subject of great interest. So, Matt has already introduced ourselves. I'm André. I'm a software engineer from the Analytics Cloud team.
Yeah, I'm Jeyvison. I picked the mic. I'm Jeyvison. I'm the currently tech leader for Forms team.
Okay. This is our agenda. We're going to talk about what are the reasons to use reactive programming in first place, what's reactive programming, and its building blocks, present some popular reactive Java libraries. What does a traditional web server, web application run on it looks like? Basically, this is a simplification, of course. It handles HTTP requests and uses a thread pool to handle all those requests. Many servlet containers like Tomcat work like that. So far, so good. It works very well for a wide range of use cases, but things start to get complicated when we need to scale to a huge number of users. And nowadays, we have many challenges that those architectures were not designed to handle. For instance, we have to handle thousands or maybe millions of requests at the same time. Unless you're building an application for, let's say, an intranet, be aware that there are over 3 billion people using the internet. Now, imagine our app becomes very popular. It's a success. And a slice of that population wants to use application. Let's say 1% of 3 billion people. It's a lot of users. You're going to need lots of threads. You also need to serve faster. The more a website or application takes to load, to respond to requests, the more users and customers we lose. The application also has to sustain heavy loads. Imagine you launch a marketing campaign. It's an outstanding success. Everybody's happy except your servers that now have to handle a much higher traffic. Whenever we need to scale what we do, we throw more servers with more CPU, more memory, but there's a limit to that, maybe economical or ecological limit to that. We can't use just more server, more CPUs to compensate. The hardware we have available is already powerful, very powerful. We just need to make better use of it. So, for instance, let's imagine we're building an application that has to handle 100 concurrent connections. What will be the size of thread pool? 20 maybe? How many cores would we need? 16, perhaps. And we need to scale that application to 1,000 connections. What will be the thread pool size? So 200, we'll need 32 cores, maybe, and 10,000 connections. And go on, 2,000 threads, 138 cores. And finally, we get to a limit that we don't know if a server can handle that, 100,000 connections. Unless we have a very powerful server, it probably would blow. So threads are not so lightweight after all. In Java, by default, we have 1 megabyte for each thread, for its stack. We also need to consider switching between threads. There's also time spent switching between threads. There's also the problem of thread starvation. One thread may, for some reason, get a lower priority than the other ones and may receive less CPU time. It may just take longer to process or just be stuck. As I said, thread pool dimension is tricky. There is no silver bullet to know what's the ideal thread pool size. There is no exact formula for that, because it varies because of the workload. Workload can be very different from application to application. And we have shared memory pitfalls. When we start to work with so many threads, we want to share data between them. People tend to use synchronization to avoid problems, but there's a cost with that too. So there's got to be a better way to use so much threads. Let's try to avoid those threads in the first place. Way to accomplish that is with non-blocking. A question to help define non-blocking. Would you ride a drive on a jammed 8-line highway or ride a high-speed maglev train? That's the idea behind non-blocking. And because we have a limited number of threads, in many cases just one single thread, blocking is not an option. So all I/O input-output must be handled asynchronously. It's pretty easy. We get rid of those threads, and it's solved the problem. We just don't block. Let's see. Here we have asynchronous code. All it does is to fetch data from a database, customer data, and it generates reports from an external service and send those reports via an external service. This code is linear, easy to understand, but blocks. It blocks in those 3 points. Let's try to fix that. This code does the same, but it uses callbacks to accomplish non-blocking. It's a bit harder to understand. We have here 3 nested callbacks, but it doesn't block. But unfortunately, it requires synchronization in this case. We need to synchronize a result to count the errors. It's just an example to say that callbacks are not the final solution for non-blocking. There are challenges too. So again, there must be a better way to handle that. Maybe declarative programming? Yes, it's very straightforward. We have here just Java 8 streams and operations. It's much easier to understand, but still blocks at that count. Besides that, we also have I don't know, it's a problem. We have this detail. We are using a common pool. It's thread pool, so we're back to the web servlet container. We're using threads after all. We may pick a different executor or scheduler, or in this case, use an event loop. If you've never seen an event loop, it works like that. It takes events from a queue and dispatches them to event handlers or I/O operations. All of that, in many cases, using a single thread. As you may have heard, never block the event loop because it uses a single thread and everything will be stuck. All these libraries and platforms use event loops. I think the most popular one is Node. It's very known for its single thread approach. We also have Netty for Java. It uses an I/O. So after all, what's reactive? From the dictionary definition, something that's reactive, it shows a response to a stimulus. It acts to a situation instead of creating or control a situation. The reactive manifesto, it's a proper definition, it's more complete, but basically it states 4 main attributes. It's an application that is reactive, it must be elastic, it responds to a varying workload, it must scale up and down as necessary, it's responsive, it keeps responding no matter what errors may come, it must detect those errors and deal with them. In case of failure, the application should isolate the fault component and avoid cascading those errors. And it's message-driven. It uses sync message passing to accomplish isolation and avoid coupling. I know it's starting to get a bit confusing, lots of concepts, but let's focus on reactive programming. There's a much bigger subject there are reactive systems. It's more concerned about architectural patterns. There's also a design patterns, but reactive program is more concerned about implementation and also a few patterns. Definition of reactive programming is a form of declarative programming that's concerned with data streams and propagation of changes. So I'm calling Jeyvison to present you the building blocks.
So guys, now, as André said, we're going to talk about the building blocks of reactive programming. The first one, events. An event is an action, is a response to an action that just happened or a condition that is just met. For example, if you have a button that we click, an event is generated by that. It is a response to the click of that button. Taking this code as example, this is an HTML button, and we have a callback function that will be executed as soon as it's the button I click, and will show this alert message. We can think of events as a stimulus to which a system reacts. So that's pretty much what an event is. But first, we need to make we need to state a difference between event and messages, right? Events. An event propagated to whoever is listening. An event doesn't care who is listening, who is interested in that particular action. It just propagates. It generates and goes to whoever is listening to it. A message is addressable. It has a recipient. When we're talking about reactive programming, we're talking about events. When we're talking about reactive systems, we are talking about messages, right? The second building block is callback. Now, we can have this code as example. We make an HTTP call. And as soon as you get a response, this callback function is executed as success or as failure. But we need to keep an eye open about callback hell. Sorry, am I talking too loud? I need to try to keep it low. We need to keep an eye open for the callback hell, because our code can quickly turn into something like this, right? It's unmaintainable, it's hard to read, it's a mess. So, but there is a cleaner way that we saw with André that can help us with it, that operators or declarative programming, right? We can do the same that was doing the previous code, but in a much cleaner way, in a much maintainable way. So speaking of operators, we have another sample. Just a quick note, these samples use push streams. Anyone here knows push stream, knows what is push stream? Push streams is an OSGI specification that is available on OSGI R7 that deals with asynchronous code, that deals with reactiveness. It's available in OSGI R7. That is already merged in our portal, so it will probably be available on 7.3, on 7.2, sorry. So what this code is doing, we imagine that we're throwing a party in our house, and we want to count how many beer, how many alcohol we need to buy to our guests. But we don't want to serve alcohol to underage, right? So what we're doing is we map those gases, we transform those gases into their age, and then we filter with gas or with age is 18 or older, and then we return a promise of a long. So this is another example of declarative programming. Speaking of streams, streams are a sequence of ordered items. You can think of a stream as a continuous flow of data that you can handle. And this is a very good way to show what we're talking about when we're talking about streams. Let's consider this first arrow. This is our gas list or our gas stream. And then we operate a map, or we make an operation of a map transforming all these gases into ages. And then we filter those ages, and then we return that count. Every operator returns a new stream. It assures the immutability of our streams. But all those patterns, all these building blocks that you're talking about, are based on this, on the observer pattern that most of us are might be aware. So it's quite straight. So we have an observable or a publisher, and we have two observers that are subscribers.
There's no problem.
Yeah, that are subscribers. But imagine that the publisher is emitting too many data, more data than the observer can handle. There's a way that you can deal with it that's called back pressure. Back pressure is the property of the, imagine that we have all this data and our subscriber can handle it, right? It's too much. Back pressure is the property or the ability of the subscriber to tell the publisher to slow down, that can handle that much data. There are two common strategies talking about back pressure. That's throttling and buffering. The first one is buffering. It buffers in memory the events that overflow. If you don't provide some threshold, it might lead to out of memory error. For example, we have a publisher, the upper stream, and it emitted 2 items. And our subscriber, that's the downstream, requested just 1. You can see that the 30 item from the buffering emitted just got buffered in the operator, and the first item is gone. It's already emitted. So buffering buffers all the data on the published side or on the memory, so the subscriber doesn't have to handle it all at the same time. For example, here. And there's throttling. Throttling keeps only the last item emitted. So, for example, the publisher emitted 2 items, but just the item number 2 is buffered or is in memory, and the subscriber requests some item. Only the second item is sent to it, and so on. Yeah, enough theory. Let's see some code. We're going to talk about Vertex, Reactor, Project Reactor, and RxJava. RxJava is an implementation of Reactive extensions. There is a library. It works Java 6 or later. Supports some languages like JavaScript, Scala, .NET. It's supported and extended by other libraries. It's heavily used on Rx Android. The Rx Android is a very popular for mobile development, and it features more 70 operators. That's a simple code using an RX HTTP client that does a GET request and uses a map to transform the result that comes from that request, and then returns a single result or an error. Some pros: it has a compacted code. Yeah, you don't need to write a lot. It's supported by many libs, but there has some cons. It has a considerable learning curve. It's not that straightforward to learn it. It's a kind of hard to debug. The documentation is not that good yet, and does not support Java 8 functional interfaces. Right. Another one is Project Reactor. Project Reactor is a library. Oh, sorry. It's a small library. It has an API very close to Rx. And Spring 5 depends on it with every function Spring data. Spring uses it heavily since the version number 5. That is an example of code with Project Reactor. We have a flat map. We have a flux. There is a stream of many elements, 0 or many elements, in a mono that is just a 0 or 1 element that returns a filtered result. Some pros: it's well supported by Spring developers since Spring uses it heavily. But the cons is that there's no much presence out of Spring. So Spring uses it a lot, but it's mainly used there. There's no much presence out of it. Now about Vertex. Vertex, I took it with a small core. It has an actor-like deployment, something like similar to Akka. Does anybody here know Akka? Okay, Akka is another library that addresses distributed processing. And runs on JVM, supporting some languages, and it has a Fluent API. And the difference on this one is that it's packaged as an OSGI bundle. So you can use it as an OSGI bundle with your bundles. Okay? There is an example of code with Vertex. Here we are reading a data file, a text file, and we are just printing the result. You notice here that we are using a callback, right, to read the data. So some pros of Vertex, it has many extensions that you can use. It's easy to distribute processing across different machines because it has verticals. There is something like actors that you can distribute the processing between nodes. So it's very nice and has a very, very good documentation. The cons, they use callbacks. So remember, I said we have to be careful. When it's not much a con, but we must be careful when we're using callbacks to avoid callback hell. Yeah, but there's one specification that binds now, that reactive streams. It is an API specification that's part of Java 9. It has this main interface called flow that has processor, publisher, subscriber, subscription. And it's all about interoperability. So all these toolkits, libraries that we talk, they are interoperable with reactive streams. Okay? Super cool. But where do I use it? Large-scale connection concurrence. External CFC calls, mainly external CFC calls. When you're doing an external CFC call, you can use the reactiveness to achieve it. Write concurrent message consumers between components inside your application or outside of your applications. You can have an abstraction of synchronous APIs. But that's not the silver bullet, as it may seem. Sometimes blocking is the only way. For example, you have to get a database connection, right? A database connection, that is blocking. Sometimes blocking is the only. Sometimes blocking is the only way. Threads are not that evil. They still can handle thousands of concurrents if they are handled properly. Coroutines and fibers are alternatives, very nice alternatives to threads. Debugging declarative code may be harder because some IDEs maybe don't have the. I think most of IDEs don't have a very good support to it yet. Data processing, that's important. Data processing is not even processing. If you are processing too much data, there are specific tools for it. For example, Apache Hadoop, Spark, that you should be using instead of plain reactive programming. So please rate this session. Don't forget if you can. And thank you very much.